Welcome to today's lecture. We are going to see about convolution, which is a very important tool that's used in finding the response y of t of a system to an excitation x of t if we know the system impulse response of a function. So when we have a system that we know has a transfer function or an impulse response, and if we give this system an excitation x at t, and if that excitation results in an output of y of t, then we know that h at t is called the impulse response. That's basically something that characterizes the system, and for that system, if we give an input of x of t and that results in an output of y of t, then we have this relationship or this expression which sets up a relationship. Y at t is essentially the integration from minus infinity to infinity of x at lambda and h at t minus lambda d lambda. So this is called the convolution integral. This expression is what we call convolution integral. This is a very important concept in communication, in control systems, because when we have a system that responds as h at t for impulse function, then whatever input or excitation we have, then it is possible to find the output by using this expression, which is a convolution integral. So what does this convolution integral involve? Before we see what it involves, the mathematical symbol for this is y at t is equal to x at t convolved with h at t, or because convolution is commutative, we can say h at t convolved with x at t. That gives us y at t, which is the same thing. So this is the commutative property of convolution. And moreover, as we can see here, convolution involves taking the input of the excitation and then time shifting the transfer function and integrating them. So if I can write the steps involved in convolution, if we see the steps involved in convolution, the first one is time reversing of signals. Time reversing of signals. For example, in that case we had h at t, and h at t was reversed to h at minus t. So in terms of graphs, if h at t is, for example, this value here, then we are going to reverse that and bring it to this side. So that's called time reversing it. And the second step is we are going to shift it. By shifting, we mean the h at minus t is going to be shifted into h at lambda minus t, which means we are going to add lambda. So originally we had this, and then it will be shifted here, or it will be reversed here, and then that will be shifted again to this side. So first this was reversed and then shifted to this side. That's represented by lambda minus t. And then we are going to multiply it point by point. which is basically the other name for integration, multiplied point by the second signal. So when we do that, as we have seen here, these two are going to be multiplied point by point. That is represented by x hat t multiplied by h hat lambda minus t. And then the final step is integrating that, which is basically summing it. So we are going to integrate from minus infinity to infinity of x hat t, or x hat lambda, and h hat lambda minus t d lambda. So that will give us integration, or convolution I should say. So in this case, why does we talk about convolution in a Laplace transform? Why do we talk about convolution in a Laplace transform chapter? Because, as we have seen, y at t is equal to x at t convolved with h at t, and integration wise it is represented as x at lambda times h at lambda minus t d lambda from 0 to infinity, or if we are going to take for t greater than 0. And if we take the Laplace transform of everything, then the Laplace transform of y at t is going to give us the Laplace transform of this integral from 0 to infinity x at lambda times h at lambda minus t d lambda. And that gives us a very unique property, which is y at s. The Laplace transform of y at t is y at s, and the Laplace transform of this whole thing can be proven to be the product of x at s and h at s. That's what makes convolution in S domain very interesting. So as such, what we are saying here is convolution in time domain is equal to product in S domain. So in order to find the convolution in the time domain, we have to integrate it from 0 to infinity and time shift and reverse it. But in Laplace transform, if we can find the Laplace transform of the excitation and the impulse response, then by just multiplying these two functions, we can find the output of the signal. So in that case, if we can find the inverse Laplace transform of, which means from this relationship we know that y at t is equal to the Laplace inverse of x at s multiplied by h at s. So as long as we can compute the inverse Laplace transform of the product of the two, then we do not necessarily have to pass through all that integration. For example, let's see if h at s, which is v naught at s as we have seen previously, over vi at s is equal to, say, 10 over s plus 5. And if vi at s is equal to 1 over s, then what is vi or v naught at t? So this is the same system as we have seen earlier. We have h at s here, and v naught at s, vi at s is given. Now we have here v naught at s, and from v naught at s we can compute v naught at t. So when we have a problem like this, how do we solve it? And we know that vi at s is equal to 1 over s, means v, small v I should write, small vi at t is a step function, right? Because this is the inverse of a step function. And we also know that h at s is equal to 10 over s plus 5, essentially gives us h at t, which is the transfer function in time domain, is going to be 10 e raised to minus 5 t u at t. So we have already found that one, and now if we use our time integral, then v naught at t is going to be what? From 0 to infinity of vi at lambda h at lambda minus t d lambda. Okay, we are interested in t here. So what do we get here? We are going to find from 0 to t of vi at lambda. Here we already have u at t, so we have u at t multiplied by 10 e raised to minus 5 lambda minus t. So this d lambda. So this expression is going to give us, we will take e raised to minus t, integrating from 0 to t of e raised to 5 minus 5 times minus t, it will give us minus lambda. This one is t minus lambda. Okay, so we have already got minus 5 et there, so we have t lambda, and that's going to give us 2 times 1 minus e minus 5t u at t. So this is our v naught at t by using the formal integration method of convolution. But how can we solve the same thing using Laplace transform? So we know that v naught at s is equal to h at s multiplied by vi at s. So that's going to give us 10 over s times s plus 5, because vi at s is 1 over s. So this has got to be some constant a over s plus some other constant b over s plus 5. So if we solve this using inverse Laplace transform, we will find a is equal to 2 and b is equal to minus 2. So this is the same as 2 over s minus 2 over s plus 5. In which case we can simply compute v naught at t is going to be what? 2 over s is the inverse Laplace transform of 2u at t, and that one is minus 2 e raised to minus 5t exponential function u at t. So this can be simplified into 1 minus e minus 5t u at t. So rather than doing the integration as we have done it here, using the Laplace property of convolution gives us the result in a very short time. So that's what's called convolution. So when we use convolution of a function, always remember that we have a function h at t. H at t is the impulse response, and we have an excitation x at t, which would finally result. So you can treat this as a black box. This is a black box. You may not know what it is made up of, but you just know the transfer function. And for any transfer function h at t, if you give it x at t and if the result is y at t, then in time domain this is basically 0 at t, or in the general sense we can take minus infinity to infinity of x at lambda h at t minus lambda d lambda. But in Laplace, if we transfer everything here, then that clearly will give us x at s given into h at s. If it gives you y at s, then in Laplace transform, y at s is always going to be a simple product of x at s and h at s, which means y at t is going to be the Laplace inverse transform of x at s multiplied by h at s. So that gives us the result. Okay, so let's see just a little bit of the some other problem, or before we see a problem, what it means to take the time shift of a function. So just as an example, if I have, for example, here x1 at t, if x1 at t is represented by a curve like this, and if x2 at t, let me draw that with a red pen, if x2 at t is represented by a red pen like this, where this is 2, this is 1, that's x1 at t, and it's going to be convolved with x2 at t, which has 1, 2, and 3, and here if it is 1, then graphically convolving x1 at t with x2 at t, as we saw it earlier, involves reversing, time shifting, and multiplying that. So in this case we are going to have multiple points that we are going to multiply x1 and x2 with. So relationship wise, we have already seen that the result of this function, which we can say y at t, is going to be x1 at t convolved with x2 at t. So integration wise, this is represented from 0 to, or from minus infinity to infinity, of x1 at lambda, x2 at t minus lambda d lambda. But graphically, what does that look like? So in graphical sense, we can divide these time shifts here into 3 or 4 regions. And the first one is for the region from 0 to t to 1. So what happens between the region from 0 to t to 1? So if I see the first one, x1 at t, if we are going to convolve x1, then x1 is going to be, first of all, let's say in this case we know that this is the same as, this is essentially, it has the same result if we take minus infinity to infinity of x2 at lambda, x1 at t minus lambda d lambda, because we know that this is equal to x2 at t convolved with x1 at t, right? Because convolution is commutative. So that tells us that x1 at t from this, which is 2 and 1, I'm going to shift it or reverse it first, so it will be reversed, which is minus 1 here, and then it's going to be shifted. By shifting, I mean I will shift it by t. So in that case I'm going to have t minus 1 and t here, as long as that gap is 1. So that's going to be x1 at t minus lambda. This is x1 at minus lambda. This is x1 at lambda. So I'm going to add this curve here, and I'm going to shift it in time. So if I shift it, for example, for this, for 0 to t to 1, what's going to happen? For x1 at t minus lambda, I have that here, which has a value of 2, and then I'm going to have this with the original function, with the red function, and the red function, this is, as we have said, t minus 1 up to t, and x2 is still at its place. I have that here, which is 1 and 3 and 2 here. And if we integrate 0, because they don't have anything common, it is going to give us 0. Alright, what about for the second position, for t between 1 1 and 2. What would the graph look like? So the graph now, mind you, we are shifting this, we are shifting x1, so x1 will be shifted here by 1. Previously it was between t minus 1 and t. Now it's going, still it is going to be between t minus 1 and t, except now it's going to be partly, or I should use that red part. So I am going to have that, and this is x2 at lambda, and this is x1 at t minus lambda. So what will be the result of that? The result of this for between t1 and 2, if we are going to have that common area, and that if you integrate will give you this. So we are just going to continue to do that. Next for 2t3. So in that case I am going to have x, I'm going to shift this more, so still this is t minus 1 and t, but the red one is going to be here now. I'm going to have here 1 and 3, and here I'm going to have 2. So now the common parts are a little bit more. So in that case, between 2 and 3 I will have this, the integration value. So this is just to let you know what convolution really is. We have a function x1 at t and a function x2 at t. So if the convolution of these two gives you y at t, what convolution does according to that x1 at lambda, x2 at t minus lambda is, it will shift, or it will reverse it in time domain, and then it will just slide it through the time. So what we just saw was, if this is x1 and if this is, for example, x2, then we are going to shift this x1 into its reflection and then move it this way all through. So for multiple points we are going to have a shifted one and convolved with this plus, and then a shifted x1 convolved with this plus, a shifted x1 convolved with this. You see, here x2 did not change. x2 is, or x1 is at its position, if we call this x1 and this x2. But x2 has been shifted, so x2 has started from this point, and then it shifted here, and then it shifted here. So that's what we are going for. By integration, we are making this sum infinitely many so that we would reach a better result. So convolution essentially takes one signal, it reverses it, and then it shifts towards here and adds it with the other signal at every point. That's basically what convolution does. So, as a second example, if I have a curve, for example, if I have this curve to be convolved with, say, this curve, then what would be the result? First I will convert this one, I will reverse it, so it will be like that, and then I will shift it, so the shifted part will come here, and then I will integrate that every time with this. So the first point, for example, I can take the shifted part with original here. So I will take the common part plus, and then I'll shift this again. So I will shift that one, but the second will remain the same, and then I will shift this again, but the second one will remain the same. So it's essentially taking the integration or the continuous sum of one of your functions, which is in this case the stationary function which does not move, it's always there, plus the other function which is moved. So this function has been reversed and moved, so it might have started from here, now it is here, now it is here, now it is here, it just shifts, and that's represented by t minus lambda. This is very important in communications where you have an impulse response of a certain medium, or it might be a channel with a certain impulse transfer function, and what is output when you have a certain input. So mind you, this is not the output for this function, this is output for an impulse function. So when you have an impulse response of that, giving it another excitation of x at t will result in y at t. How do we find that value? It's using convolution. So convolution in time domain is integrating x at lambda by h at t minus lambda d lambda, or it is the same as h at lambda and x at t minus lambda d lambda. But if we use Laplace transform, then y at s, y at t would be, because y at s is x at s multiplied by h at s, y at t is basically the Laplace inverse transform of x at s times h at s. That's the beauty of using Laplace transform, because it is much easier to use Laplace transform to find the output convolution wise than using the time integral. Thank you very much for attending this lecture.